In this video, we'll be going over reaction mechanisms and acceptable proposals for mechanisms, and then we'll be going over reaction mechanism terms, and then finally, we'll go over a couple example problems, and then we'll finish off with an energy profile question, kind of like a summary, kind of like a rate summary question. Okay, so mechanisms um, are try to describe a reaction and how it happens in what are called elementary steps. So a chemical reaction, a lot of times, when we write out up until now, like we'll see like a reactant A plus reactant B, and it creates like product C plus product D. Okay, so and a lot of times, so that's up until now, we've kind of just been interested in what these look like and their energy profile, what they look like, and then what the beginning state versus the final state, and then we could get like the change in energy, or if it's done at constant pressure, the change in enthalpy. However, a mechanism, what it tries to do is it tries to describe what's going on during this segment, like kind of like during, you could think of it as like what's going on during the arrow. And so mechanisms, they show what are called elementary steps. These steps that are not really like reactants and products, but like these sometimes very high energy intermediates that are unstable that go on to react, and then they finally form the product. So it's kind of like they show like these intermediate steps or species that aren't reactants or products, and they're called intermediates. So some mechanisms can be like 12 steps long. Other mechanisms are 2 steps. Some are just 1 step. It's actually the overall reaction is the actual mechanism. So the elementary steps, these ones that like don't really aren't really stable for very long, they're called elementary steps. And most of this I think you'll get the hang of more when we start looking at examples. So these are called elementary steps, or elementary, I've seen them referred to as this elementary reactions. The overall speed of a reaction is determined by the slowest elementary step, and this has a name. It's called the rate determining step. It's kind of like if you're stuck in traffic. So this is sort of like, if, or let's say you have a specific route you take when you go home, like you make a right turn, and then you go straight for several miles, and then you get on the freeway, and then you head like northeast. Okay, and then you take an exit. So here's the freeway, and then you take an exit. Okay, and then you need to make like a left turn, and then another right turn, and then you're home. So a reaction mechanism is kind of like you're at work or school, and then you try to get home. So work or school is kind of like the reactant, and then home is like the product. And so these elementary steps are all the little things you have to do in order to get there. One of these is going to be the slowest one. So perhaps on your way home, perhaps this part where you go on the freeway, perhaps this is like really a popular route and it's really crowded. So this might be like the slowest step in going home. So if this were a reaction described by all these steps, this reaction would have 6 elementary steps, and none of them are too bad except for this when you're on the freeway, and then that one's like the worst one. So that would be called the rate determining step. So it determines the overall. It has like the by far the biggest impact on the overall rate of the reaction. So that has a name. It's called the rate determining step. Um, Now, an acceptable mechanism. So these are what I mean by acceptable is like these are proposed. How like scientists will try to describe how a reaction happens, and they'll propose a possible mechanism. Their possible proposal, it needs to satisfy a couple of requirements. One is the sum of all the elementary steps. The sum of all the elementary steps need to result in the overall reaction. So it's kind of like what we saw before. It's kind of like Hess's law. So this is sort of like where you take several reactions, and then you combine the if you see something the same species on the reactant side, then you combine them in terms of like a coefficient. Um, and so let's say you have like 2A plus B and it makes C, and then in the next reaction you have like A plus D makes E or something like that. So if you're adding these up, it would be like 2A's plus one of these. So in your overall, it would be like 3A's. So the sum, so it's kind of like Hess's law, where the species are additive and they show up as coefficients. And the other requirement is the rate determining step or the slowest step. It needs to agree with the experimental rate law. So what this means is the coefficients of the slowest step must match the exponents of the of the slowest step. Oh, I'm sorry. I just said that. So the coefficients of the slowest step must match the exponents of the rate law, which is determined experimentally. Which is determined experimentally. That's one point to never forget is I'll put in brackets here. So rate laws are always determined by experimental data. So for example, the method of initial rates. So I'll put usually by the method of initial rates. So we'll need to practice this, like what this is saying, because this is an important point here, and you'll see we'll go over a few examples. Um, okay, so here's an example. So for the reaction, 2 moles of hydrogen gas reacts with 2 moles of nitrogen monoxide. It makes nitrogen gas and 2 moles of water vapor. So the observed rate law is this. Okay, so this is determined by experiment. This is determined by experiment. Now, here's the question. So, which of the following is an acceptable mechanism? So, mechanism one, there's only one step. This is our elementary step. So, we're trying to propose that this reaction occurs by the only elementary step actually matches this exactly, the overall reaction. So, so if we look back and see the requirements, so we'll go back a slide, and the requirements is the sum of the elementary steps results in the overreaction. So we see that the elementary step is only one step, and it matches it exactly. So next we need to see do the coefficients of the step match the exponents of the rate law? So let's take a look. So so that means that this two and this one they need to match here and here, and then we actually see that they don't. So the nitrogen monoxide actually matches here. Okay, um however the H2 doesn't match. We see that this is a 1 and then this is a 2, so this doesn't match. So the coefficients don't match the rate law, so this can't be an acceptable mechanism. So this doesn't work. Okay, let's check the next mechanism. So we have several steps here. We have 3 steps, and one of these is the slowest. And so let's add these up and then see if it matches this. That's the first thing that we need to check. So again, let's go back one slide. And what we're doing is we're checking this, okay, the sum of all the steps, if it matches. Okay, so we have three steps. So let's add, okay, let's see. We see that this right here, this will cancel with this. And there's a name for that, a species that's produced in one step and consumed in another. We see that that cancels. We also see that this oxygen cancels with this one. And then now let's go ahead and add the remaining species. So we see that we have H2 here and another one here. So that means we have two H2s, and we have 2 moles of NO, and we have 2 moles of H2O, and 1 mole of N2. So does this end up matching the overall? It looks like it does. So that actually checks out. Now the next thing is we need to match. So we're going to go back to this slide again here, and we're going to check this. So does the rate determining step or the slow step, does it agree with the evidence of the rate law? So we're going to match the coefficients of the slow step with the exponents of the rate law. Okay, so the coefficients of, so here's our slow step, and we're gonna match this, so that we see that we have a 1 here. I meant to write a 1. So 1, and it matches with the 1 here, but then we have a 1 mole of NO in our slow step, and we have 2 in the rate law, so this doesn't match. Okay, so this 1 right here, this, the coefficients don't match. So the coefficients of the slow step don't match the exponents of the rate law. Okay, so this doesn't work either. So mechanism 1 doesn't work and mechanism 2 doesn't work. So the only way they work is if they fill those two requirements. So let's check a third mechanism. We see that this N2O will cancel with this. And then I think that's the only thing that cancels. So let's go ahead and add everything here. So 2 moles of H2 plus 2 moles of NO, and we get 2 moles of H2O plus 1 mole of N2, and this matches. And our rate law was this. It was 2 NOs, so it's second order with respect to NO, and then first order with respect to H2. And so let's go ahead and see if this one matches. So the 2 right here, it matches the 2 there, and then the 1 here matches this one. So both requirements work. So this is, so we would say that this third one, this one right here, this is an acceptable mechanism. So that one works. All right, so let's look at a couple terms. So there's some terms that describe the overall what's called molecularity of this. We would say that when we look at these exponents here, what they actually mean is it's said to mean that there's 2 molecules of NO are required to collide with every one of these. So it means like 2 NOs must collide with one of these, and they all need to collide with the correct orientation. So here's my collision here. And then this is how you determine the overall molecularity is you add the number. So these exponents are additive, and that's how you determine the overall what's called molecularity, which is on the next slide. So the sum of all the exponents in the rate law gives what's called the molecularity. So here's a couple examples. And like I just said, molecularity refers to how many molecules are involved during an effective collision. So unimolecular is one molecule. So if your rate law equals this, and then you just have one, then this is called unimolecular. If you have a bimolecular reaction, 2 molecules are said to be involved, and this is an example, and this is another example. So you could have like two moles of A and then they decompose and then they make B. So if that's your slow step for a certain reaction, or you could have one of each, and that would be two molecules. Or you could have what's called termolecular, and this is supposedly rare because it's really difficult to have three molecules all collide simultaneously at the same time. So here's a couple examples. So if I add two and one, that's how I get three molecules are involved, or something like this. And remember, this all refers to the slow step. So remember, molecularity refers to the slowest elementary step, or what's called the rate determining step. Okay, so let's look at another practice problem, and we're going to work with a couple of terms, like what's an intermediate, try to identify an intermediate in a catalyst. So here's an example problem. So this question says which species is an intermediate and which is a catalyst in the following mechanism. So here's ozone reacting with nitrogen monoxide, and it creates nitrogen dioxide and oxygen. And in the following step, the nitrogen dioxide actually is consumed. So it's produced here and then consumed right away in the next step. And this reacts with 1 mole of unimolecular oxygen, and it makes nitrogen monoxide and O2. So um, the first thing you do is add up these steps here. I'm gonna kind of start this question, and then I'd like you guys to finish this off. So I'm gonna start this and give a few hints here and there. So if I take the O3, I'm trying to come up with my overall reaction. O3, you see that the NO2 cancels right here, um, and you see that the NO right here actually it actually starts here. It gets consumed because we don't see NO over here on this side, but then it finally actually gets reproduced here at the end. Okay, so this isn't going to show up in our overall. This actually cancels here, but there's a difference between this one and the NO2, and that's kind of the point of this slide. Is I want you guys to try to decide what that is. Okay, so my overall reaction would be this. And I'm going to write a couple notes here. So um, I'm going to say the intermediate. So here's a couple of terms. So intermediates are produced in one step, and they are consumed in another elementary step. And a catalyst is not produced or consumed. So a catalyst, it needs to be there at the start of the reaction, and show up at the end of the reaction. So here's my question for you guys is which one is the intermediate? Which species, or actually just try to answer this. Actually, it's written up here already. So I want to see what you guys come up with on this question. And now let's go to one more question. It's a practice question with energy profiles. So here's a couple energy profiles, and as you see, we see the energy level, the potential energy that you started with. So this would represent the reactants, and this line right here represents the potential energy of the products. So as we see, um, this from here to here, this represents the change in overall energy of the reaction, um, and right here is actually the forward reaction. So from here to here, from this point, so what you started with to the top of this hump is the activation energy for the forward reaction. And if this reaction were to go in reverse, if this reaction were to go in reverse, like let's say these were now your reactants and these were your products, then you'd be starting way down here, and then you need to go over the same exact. You'd have to cross that same hump. So in the reverse direction, your activation energy would be from here, what you started with, to the hump here. So your activation energy for the reverse reaction is what I drew in red. So this distance from here to here. Okay, so with that said, let's go over a couple of questions here, and I want to see what you guys come up with. So this says rank the reactions from slowest to fastest, assuming they have nearly the same value for frequency factor A. And if you recall, let me write the Arrhenius equation. So here's our rate constant, and it's this frequency factor A times e to the negative EA divided by RT. So we want to kind of use this and apply it to what you're seeing in these energy profiles to answer these questions. Okay, and two, try to answer this. Which of the following statements is or are true? So the activation energy for the forward and reverse reaction can be different. Assuming that A is constant, if both EA and T increase, then K will increase. So is that true or false? And then is this statement true or false? For two different reactions, the one with the smaller value of EA will have the lower value of K. So I want to see what you guys come up with for this question and the previous question on the previous slide. Okay, and that concludes our tutorial.